Hello and welcome back to week 4 of NLP, where we're moving over to, if you see this book right here. So far in the course, just to kind of recap, I broke this down to 3 major parts. The basic idea is of big data. I have some supplemental stuff I'm going to share with you too here in a minute. But the basic fundamentals of big data. Big data can be used for anything. In the past, I mean, 2 or 3 years ago when we talked about big data, we generally talked about tabular data, things you'd find in Excel. Now, because of ChatGPT, LLMs, and technologies like this, we're going to more unstructured data. So that's why the course has kind of shifted. That's why this course has taken me a lot of time to design and develop, because in the past, we traditionally used mainframes, supercomputers, Linux to process that tabular data. But the world's evolving, and that's why this class I feel is so vital to your education in the future. So I want to give you a good foundation of large data and the changes in it. So that was the first, I guess, 3 weeks was the basics of big data, some of the problems with big data, how fast does it come in versus how much volume does it have, things like that. Now we're going to deal with a little bit more of NLP. Natural language processing is the idea of, they call it unstructured data, and I really don't like that term for this. It is technically unstructured data because it's not in a tabular format. Now, sometimes you'll get the data in tabular format, but it won't say, here's all the nouns, here's all the adjectives, here's all the pronouns. You don't get that. Maybe you get the author and then a column with a bunch of data in it. And this unstructured version or this unstructured data can be a little bit more difficult to work with. There is, I don't want to say there's no hard and fast rules, but there really is a lot less hard and fast rules when processing this. I mean, it almost seems counterproductive when we did the first 3 weeks of basic fundamentals, because there's many quotes either from Google or from different industry experts that say 80% of the information or the data out there is unstructured, yet we spent, 10-15% of the class on structured data, just learning big data fundamentals. So this is where we kind of get into text or corpus or words or more unstructured data. So for the next, I think it's 3 weeks, 4 weeks, I just finished all the lectures. I reread that whole book today. I came up with 3 different weeks of lesson plans. So for the next 3 weeks, what we're going to try to do is take a corpus of text, a group of words, and look at it. Is it positive? Is it negative? Can we translate it into another language? How do we tokenize, break down those words to individual words? What do we do with the words that have the S's on the end of it? Books versus book. So that's kind of where we're headed now. In my mind, and again, I could be wrong, NLP comes down to 2 major distinctions, or all data. You have past data, those are your data analytics guys, and then predicting future data. And I've said this before, that's data science. So right now we're going to kind of look at the past data. We're going to have a corpus of text, and we're going to say, here's how we tokenize it. Here's how we do something. After the midterm, what we'll do is we'll start doing funner things, and at least in my opinion, funner things. We'll generate new text. We'll generate new images. We'll try different models. We'll push the limits on that type of technology. Didn't advance. So again, we moved to this book, A Blueprint for Text Analytics. Again, if you don't have the books, don't stress. A lot of the stuff's online. I did pull the author's GitHub and try running some things, and literally nothing worked. I updated one of, I think it was chapter 5, his GitHub, his code, and it took me like 4 hours to update it. So I'm trying to think if there's a lot of value in sharing those with you. Since chapter 5 is done, I'll share that code with you. But if I have to spend 2 or 3 hours updating somebody else's code, I don't know, it's always worth it. I do have a lot of samples, and there is some math involved in this chapter. Now, let's talk about math. One of the things when I was a student, which I'm still a student, but one of the things that always kind of upset me as a student is when I took CS classes, they'd always hound math and not application. We're in a business college. Your goal is to get to the end result. So I try not to stress the math. Now, some of you want to pursue additional coursework in CS and data analytics and things like that. And math might be important for that. Understanding the deeper dive into that might be important. But it's not for everyone. So I'll try to keep the math as light as possible, and I'll really keep the fundamentals and the goals the driving purpose. Now, let me see if I can break that down in English. So I hate to say that. So I have a car out in my driveway 10 feet away. I couldn't tell you the compression ratio on my cylinders. I have no idea. I can't tell you the temperature my catalytic converter runs. I know it's like 1,000 degrees. I mean, I have something like 260 sensors on my vehicle, and it monitors, air pressure intake, all these things. Half of them I don't know. I mean, I know vehicles, not maybe great, but I understand vehicles pretty well. And I don't know any of those things. But yet, for the last 20 years, I've been able to drive that vehicle and countless other vehicles, trucks, cars, motorcycles, motorbikes, electric vehicles, without a problem. Because I have a goal of taking me from here to where my destination is. Exactly. That's what that is my teaching philosophy. If you have Google Maps, we can talk about different algorithms to plot courses. We can talk about how satellites, how GPS satellites work, how other GPS satellite systems work. I mean, I used to teach in College of Engineering, and when we did those, that's what we would talk about. How do we encode signals, and how do we do sidebands? That's not what the purpose of this class is. So I don't want you to get caught up in the details. I try to conceptualize everything at a high level. So for this week, we're doing chapter 1 and chapter 4. And I kind of mix the two chapters together because it's weird the way they're laid out. I also skipped chapter 2 and chapter 3. Now, why did I skip those two chapters, Richard? Very, very straight, very honest answer. Because I'm kind of expecting you to get a data set, not to find a data set. Not to rip a data set. So, when in the business world, you have people that do rip data sets or get public data or do things like that, and they're specialists. And there's other classes that focus on this, and they're great classes. And I mean, a lot of my master's was using APIs. So they are important. But in the course of big data, in the course of NLP, I'm going to present you, or you're going to find a data set and say, hey, here's a data set, here's what I want to do with it. You're not going to have to go to a website and figure out an API. You're not going to have to go to a website and figure out how to rip it, using Beautiful Soup or these other tools. So that's why I kind of skipped chapters 3 and 4. So let's dig in a little bit. Okay. So again, we're going to work from a place where you have a data set, a database, a book, the Amazon reviews, whatever it is, you have some type of data. Those chapters of chapter 2 and 3 focus on getting those chapters or getting that data. APIs are particularly important because a lot of modern websites use APIs. But a lot of people that get APIs don't do a lot of NLP work on those APIs. So, that's just kind of how, I'm running this right now. I don't know if I used this quote in the last chapter or this last week or this week, but I just love this quote. Machine intelligence is the last invention that humanity will ever need to make. So somebody asked me to speak to a group of graduate students here at the university in another college. And one of the things I'm going to talk to them about is this basic idea. One of the things I'm going to talk to them about, like some of them are medical students, things like this, scientists. Well, we haven't been able to discover a new antibiotic in, some say 60 years. I looked it up, it says 1983 was really kind of the first new antibiotics. But yet machine learning just discovered a new class of antibiotics. Now, it's not FDA approved, it's not to market. But just think about that. machine learning discovered a new class of antibiotics. We created a tool that can find new antibiotics. And I think NLP, maybe not necessarily NLP, but we'll say unstructured data, noisy data, not tabular data, is the next big iteration. In the next 10 years, we're going to see a lot of data, a lot of inventions, a lot of information, a lot of wisdom come from unstructured data. So let's dig in. When we talk about a corpus or data, and I have a couple extra EDA, the exploratory data analysis is often abbreviated EDA, that I can share with you if you want. EDA is sometimes 80% of what we do in any type of data science. It is getting a good set of data. Because we're human, and when we input data, it's not always accurate. Even if a machine inputs data, like you have a sensor data, the calibrations could be off. So trying to get a clean, good understanding of the data you're working with is so valuable. The book lays out 3 different kind of terms that we can use to kind of define a corpus or a body of data or text. We talked about this a little bit before, the metadata, the context, and the score. Metadata is anything that kind of describes that data or relates to that data. I believe I shared an example of the NSA and the FBI, how they don't really listen to calls anymore. They look at the metadata of a call. If you call somebody for 3 seconds, it could be a wrong number. It doesn't matter what you say. Or if you call somebody for 10 minutes, that might have more value. And going down that rabbit hole, particularly the NSA and the FBI, for example, if 2 people, they're tracking the location data, metadata, and both people walk into a cafe and turn off the phone at the same time, then it happens again with the same 2 people a week later, you really don't need to know what they're saying. You know that somehow they're connected. So metadata is anything related to the data. It could be the author. Sometimes it's latitude and longitude on pictures, what camera it was shot on EXIF information. Any of that data that kind of describes the corpus is metadata. Now the context or the content is the words, the sentences, the phrases. What is the actual data? In the term of the phone call, it would be the actual phone call. Then the scores. Now, the scores are the statistics after the fact. How many nouns did we use? Maybe in some type of tabular data, how many nulls do we have? How readable is it? Okay. These are things that we calculate either from the metadata or we calculate from the content or both. Okay, on the sample homework I provided this week, I showed you this diaphragm, okay? And literally on page 4 of this book, it talks about, hey, you have a lot of data and it can be a nightmare to work with. So just a real kind of general idea or a warning or information on that. So if you have a huge data set, let's say, 100 million rows. Well, you don't want to process 100 million rows and find out you have an error. If you process out, because maybe it takes you 4 or 5 hours or 10 hours or a week. If you process out 1,000 rows, then, got an error. You can fix that much quicker than processing out a million errors. Doesn't always work, but, it does happen. I'll give you an example of this real quick, too. I started processing out clinical notes. So, you go see a doctor writes down, hey, Richard Young is a healthy male, blah, blah, blah. Well, some nurse in this state decided to start using emojis in their clinical notes. Now, I started processing out data. I had a great data set. I think I processed like 100,000 rows, no problem. Then I processed 1 million rows and no problem. And 1 million rows takes about, I think, 6 to 8 hours. So, I can start in the day and then maybe by the time I go home, it'll be about ready. or I can process it at night and hopefully the next day it will be done. Well, as soon as I processed out about, I think I capped it at 5 million, but as soon as I hit about 2.5 million rows, that's when the emoji error hit. Okay, so 100,000, I can get it done in an hour or two. A million takes about half a day. 2.5, it takes 2.5 million rows, takes about 2 days. And after 2 days, I get an error. And it drives me up a wall. I wasn't sure if it was my machine or if it was a database connection. So I reprocessed 2.5 million rows, same error. I know there's something wrong with my data. So why? Because emojis didn't exist 10 years ago. And I'm processing things longitudinally, which maybe I should have done random sampling, but whatever. So it is important to try to get a working model, a working pipeline, a working data flow. And you can use, hey, 10%, 1%. Once you get that working data flow and you know it works. I mean, I knew my data set was working because I processed out 1 million rows without a problem. So I knew there was something in that clinical note that was causing the error. Okay, so it's always kind of vital to get a working data set, even if it's small, then add on to it, and see what you can do. Another idea is how close to the data can you be? What do I mean by that? I talked about this a little bit before, but if you're working with large data sets, let's say terabytes, to download it to your home on a VPN, it could take you weeks. But if you had a computer in that data center, it could take maybe a few hours. So you want, if possible, you want to have your process as close to the compute and the data as close as possible. Okay. Now, sometimes another thing we can do is we can chunk the data. When we talked about Hadoop, Hadoop had a method for breaking up the data. Okay, but that's one method. When we talk about GPUs, sometimes we say, hey, do 1,000 rows, do 1,000 rows, do 1,000 rows, or take 1,000 rows on this machine, take 1,000 rows on that machine. Breaking up the data can make things a little bit more efficient, but it can also add a lot of overhead. Depends on the type of data and the size of the data and how you chunk it. Okay, so now another important concept of EDA is not just to see what we have, but to see what we don't have. Okay, and what do I mean by that? Because often people just wrap their head around EDA and say, hey, I have this. Yeah, sometimes that's correct. We look at a housing data set and, hey, I have all my housing values there. I have all my addresses there. But what are you missing? Sometimes what you're missing is just as important as what you have. And on that clinical note data set I was just talking about, I was missing 18 patients MRN. Actually, there was a space in front of it. So since there was a space in front of it, it wouldn't load correctly. Now that's 18 people's lives, 18 people's prescriptions, 18 people's basically medical history that if I didn't find a way to fix would be gone. And I wouldn't know about it if I didn't do an EDA, if I didn't really look into the data to say, hey, how many nulls do I have, how many errors do I have, what's going on. Other times, EDA might not be important at all. You're looking at the complete works of Sherlock Holmes, and for some reason, some words are missing, it might not affect something as nearly as much. So try to keep that in mind. And I have some code samples I wrote that I'm going to do another video and show you some of these code samples. So just keep that in mind, that EDA is not just this cut and dry, oh, hey, everything here is capitalized, everything here is 12 characters. It's kind of what is your goal, I think your book has a different method and has a bunch of things. There's something called pandas profiling. Okay, pandas profiling, it doesn't work super good on collabs, but on your local machine, it's beautiful. So basically, you can give it a data set, you load it into a data frame, you said, hey, tell me about this data set. And it will. And it does a great job. It can tell you what variables are related to each other. So if you're doing a linear regression, these two are related. It can tell you what's our nulls. It can tell you maybe, the longest field. I'll run a demo of it, and it's a very good point. It's a very good product, or a very good way to start your basic EDA. I have a little picture on there. I know it's impossible to see on the screen, but when I run the code demo, you'll see it. And I'll give you the code. You can throw it on a tabular data, an Excel document if you have one. You can download some type of data and just run it. It works super fast. It's great. It saves me from doing 20 to 30 different steps. Once I find a problem in Pandas profile, I can look into that program or that error with other tools. It's a very good starting point. I just realized I didn't change any of these pictures. Oh well. Okay, so your book doesn't really cover the general concepts. They do in chapter 4 a little bit, but let's just talk about big picture ideas. Big picture ideas. What are we going to do with NLP? If I give you a group of texts, if I give you a big book, I'll give you all the text in this book in a text format. What are some things to think about? We have to remove noise. What does that mean? That means removing HTML characters if it's in there, or special characters. Let me see if I can find an example. So a lot of times in books, you'll have a different formatted text. So you have like just a regular, I don't know, Times New Roman. Then right below it, you have like some type of italic code. Sometimes that code is formatted weird or has extra spaces in it, okay? That's a great example of noise removal. You want everything to be as normalized or as, consistent as possible. Machines love consistency. So when you have a bunch of weird things in there, it doesn't always work. Noise removal could be removing an emoji. Okay, tokenizing is the idea of breaking text, a sentence, paragraph, book, into individual words. And this is so much easier if I just show you. Basically, it puts a quote around it and says, hey, here is an individual word. Now, we start to think about this, and one reason we need to do this is because computers, machine learning models, statistic models, can't deal with words, or sentences. They can deal with maybe individual words if we convert them to numbers, but not necessarily sentences. If I ask you what 5 plus orange is, it's impossible to answer. But if I take the word orange and convert that to 12, and I say what's 5 plus orange, which equals 12, we can come up with a 17. Normalization, there's a couple different terms of that. There's stemming, making things lowercase, there's lemmings, there's a bunch of things, a way we can normalize data. Spell checking might be another one. And matter of fact, let's dig into it. So these are more of the normalization methods. So stemming is the idea of taking a word and reducing it to its root form. Okay, removing prefixes, suffixes, suffix. Oof, that's a hard word to say after a long day. So stemming is stem. Books is book. Okay, now. Lamenting, I can never say that word correctly. So, lamortization. So I said it once right. It's a little bit more complex of an idea, but we're trying to find the root word. So Richard's running to the store. So running, the root would be run. Richard ran to the store. Well, you can turn ran to run. So it's basically the base word, good, better, best, greatest. They can all be condensed down to one word, one version of the word. There's also lowercasing. A lot of times we just slam everything down to lowercase. Stop words we'll talk about. I have a demo of stop words. Stop words are words that don't really add any value to, not necessarily to humans, but to figuring out the sentence. In LLMs, we don't normally, I don't want to say that, we don't always remove stop words, okay? Spelling corrections. If you read my notes and know me, I'm the worst speller in the world. I cannot spell. I blame it on public school. But, spelling correction is something, that I very commonly do on a lot of things. The problem is, like in the medical world, spell correction doesn't work well at all because so many words are often spelled correctly, but they're not in a standard dictionary. Now, I think we dig into stop words. So stop words can be thought of noise. And I think I have a demo on the next slide. Yeah, I do. Okay, good. So one reason that we remove stop words is to trim down the size of the data set. Bigger data set to smaller data set processes faster. It can increase algorithm performance. Why? Well, because we have less noise, we have more of what we're looking for, more of the keywords, less filler words. If I had to give you if I had to give a speech, and I use yeah, uh, let's do this, those don't add value, so we can remove them. Focus enhance on relative words. We talked about that. Useful in specific applications. Reduces noise. Stop words or common words such as the, is, in, and. Sometimes they're domain specific, meaning if you're working on a particular type of domain, the addresses, I think we're looking at an Austin, Texas data set. Maybe we'll want to remove the word Austin, Texas, and any of those suburbs because they don't add, I mean, their house is in Austin, Texas. We know they're in Austin, Texas. So they don't add any real value to that data set. So I don't know if I can zoom in. Not really. Nope. Okay, so I do have this demo. We can run it in the code. But if you look right here, so I removed stop words. And it says, absolutely gorgeous 4-bedroom home with 2 full. After I remove the stop words, absolutely gorgeous 4-bedroom home, 2 full bath. So it removed the word with. Here's another example. I kind of highlighted it to make life a little easier. Absolute darling 1-story home in charming. After stop word removal, absolutely darling 1-story home, charming. So it just gets rid of those words. And I printed out the total count so you can see it. That's something I just do. I don't even think the book recommends that, but I like to know how many characters I have before, well, with the stop words, I guess, and how many characters after I move the stop word, so I know I'm actually doing something right. It's really not that hard to remove stop words. There's a couple different methods to do it. You install NLTK, you can download stop words, say, hey, I want to remove the English stop words, because again, different languages, different stop words. And then basically you throw some text in there. You see we're using Matrix and I think Grimm, because I just watched a TV show with Grimm. So those are where my text comes from this week. And we just remove the stop words. We can save it to a new data frame, we can save it to a new variable, doesn't matter. It's not this harsh in the world. Now, again, there's different corpuses or different stop word lists, but NLTK is a very common one we use. Now, you might ask, what is NLTK? That's a fair question. So NLTK is a Python package that does a lot of cool stuff. I wrote that, think like a scikit-learn for NLP. It has built-in data sets. It can do tokenization, which we'll show you here in a second. Parts of speech. Hey, this is a noun, this is a verb. It can do name entry recognition. So if you have a bunch of text and you want to look for all the corporation names, you want to look for all the countries, that's name entry recognition. Stop word removal, we just talked about, stemming and lemmatization. So NLTK is one of many, but it's one of the more popular tools that NLP practitioners use to kind of clean up their data set, do some basic stuff with, so get familiar with it. Let me load the website here. Good, load. NLTK is a leading platform for building Python programs to work with a human language. It provides easy-to-use interface to over 50 resources such as WorldNet, blah, blah. Let's see. So what are we doing here? So yeah, you can see we talked about, or we will talk about tokenization. The sentence is at 8 o'clock on a Thursday morning, author didn't feel very good. So here's how you tokenize it. I mean, it's very, very, very clean, very simple. Named entry recognition, that's to look for words like, tree, person. We'll talk about this in a little bit. I don't want to get you too confused with that. So it's NLTK, when you download it the first time, I think we did it on the last homework, even though you might not have realized, you just download it to GitHub, and you download these packets, I guess, these modules, and like software to just download. And once you got it downloaded on that particular machine, if you have your own local machine, you don't really have to download it again. On Colab, you have to download it every time you start or restart a session, but it's a great little tool. So we'll be using it a lot. So tokenization, like I said, you saw it over there. You know, it's a process, and one of the very first steps in text analysis and pre-processing, breaking words into tokens. Now you can also do the same thing with regex. Regex is much faster, but not nearly as powerful. So that clinical note problem that I had, where somebody used an emoji, I had to use regex after, I don't know, the 2.5 million characters. After I found out the error, I had to use regex to remove the special characters. So you can use regex. It's, you know, this class is not going to go a ton into detail about regex. I mean, regex is a tool that you'll need to familiarity with. And once you need regex, you need regex because nothing else will really seem to do. But I'm not a regex expert. I mean, I use it every 2 weeks, every 3 weeks to deal with a problem. But I mean, as long as you understand the basics of regex and what regex can do, you'll be fine. So regex, regular expression, and I think I have some more demo on this somewhere, is basically a language that we can make things lowercase. We can make things with a space. We can look for, it's a pattern matching, pattern recognition, pattern matching tool. If I want to look for a birthday and they have to have 4 digits followed by a dash, followed by 2 digits, I can do that in regex. Part of speech tagging, like I said earlier, NLP can look for verbs, nouns, adjectives. I did a research project at UNLV a while ago where I wanted to know if people in a cage fighting, what is it, like MMA fighters, if their speech changes before fight, particularly in high school, but before fight, after a fight, like in the cage match, and then after a fight. And I couldn't really see a difference in the speed they talked because they were breathing so heavily. But I did notice a different use of nouns and verbs and adjectives. I mean, this was like 5 years ago. But things like that can be really important. As we age, how do we use words differently? And there's a lot of research going to that. Name and entity recognition, I talked about that. Organization, locations, stemming, reducing words to the root form like fish to fish, fishing to fish. Laminarization, like I use this one, I think better to good. Let's see what else we have. Tokenization. Sorry, for some reason, every airplane in the country is flying over my house tonight or today. Ignorance is bliss. I know what you're thinking because right now I'm thinking the same. Actually, I've been thinking it ever since I got here. Why, oh, why didn't I take the blue pill? So here's kind of just, removing some of the characters, kind of making it, just before tokenization. Now here's after tokenization. You still see I have a character here I'd probably want to remove, maybe get rid of some of the semicolons and periods, but at least it's tokenized. Okay. So, I mean, now that it's tokenized, I can look for, just do find all NBSP, non-breaking space, and boom, remove those. I can remove all the semicolons in one. So that's why tokenization as one of the first steps is so important. Your book does talk about inverse document frequency, and there is a math formula. It's not really that hard. But basically, what we have to think about is if we have a big collection of words, how do we, I guess a big collection of words, a bag of words, a big collection of words, a document, how do we know what are the valuable words in there? And it's kind of the same thing with diamonds or gold. If we have quartz or some type of stone here versus a diamond here, well, in theory, diamonds are more rare, hence more valuable. Lead and gold are very similar, but in theory, gold is rarer, more rare. That's why it's worth more. It's more important in compared to each other. That's all inverse document frequency is. Okay, we look at 1,000 documents, 1,000 words, whatever you want to say, and you notice the word apple, and it shows up 10 times. Hey, then maybe it's important. We can assign a score. And we look at the word pear, and maybe it only shows one, will show up once. Okay, so we can use this type of frequency counting by the size and how common it is to say this is a kind of an important word. This is not a super important word. Okay, and we'll talk about this next week when we go into document summarization. It's how we summarize a document is by a method very similar to this. Keyword and context. That's another term in the book. I don't know if they define it or not. You know, if I said, hey, there's a man walking, you really don't have a lot of context. So the idea behind keyword and context is that what's around it gives it context. There's a man walking in an airport. Okay, now, in an airport, I have context to what the man's doing. He's walking in an airport and not walking home, not walking on campus. So keyword and context basically means that you're using the surrounding text to kind of understand the word of interest. I have an Apple computer. I like apples in the morning to eat. The context is different. The word is the same. Okay, engrams. This is kind of weird at first, but once you get it, it's really simple. An engram is basically a group of words. Don't worry about the unigram, bigram, none of that matters. If you have a tokenized text, it's generally in 1 gram. The quick is 1 word, brown is 1, fox is 1. If you do 2 grams, n equals 2, you're taking the quick, and then you're also doing quick brown and also brown fox. So you're pairing them up by 2s, or by 3s, or by 4s. Now, this helps us. It also expands data, makes processing a lot more complicated. But this helps a lot because now we can kind of understand what words may go together, what words might not go together. Apple computers, engram of 2 is very logical and useful, where ripe apples, we have different contexts. So that's why these engrams are so important, such an important concept. Of course, I just said that, and right here I made a slide. Contextual meaning. They help understand the context of a meaning or words in a sentence. Okay, 1 engram only sees individual words. 2 grams or 3 grams or 4 or 5 can capture a better understanding of the context. And this is with an example. I use Apple, but I guess I should have used bank. River bank or savings bank. Very, very different. And really the only way to kind of understand it is to pair those 2 words together. And when we look at predictive text and autocomplete, think about this. Richard's going to the river, then it knows bank. Richard's going to deposit money in his savings, I guess it would be account, would be more natural. I think I have some code. I don't think I included it in this lesson, but I do have some code to kind of do this predictive modeling. But now you can see why engrams are so important. Okay. Also trend analysis, things like that. So, yeah, limitations. Larger ends can handle data sparsely prone, where most engram combinations are unseen or rare in training. They do not capture long-term dependencies. So, a long-term dependency like that means that, I guess I should move a picture of my face somewhere, but if you have something that's 10 words over, then an engram won't capture, there won't be that relation. Richard, comma, is often a good person, comma, who goes to a bank a lot. There's that gap in there. But now engrams are very simple. They're easy to do. They're great at capturing local context of words. So your book talks about changes in frequency over time. And I think they use like a UN speech recognition, and they look at certain words over time. Nuclear, terrorist, and I wish tracking words over time was that easy. I've had to do it a couple times, and it's never that easy. And I don't know really how important it is. Okay. Now machine learning can do a little bit better. It's more common to create these creating frequency heat maps, as you see on the right. This right here. There's no little laser pointer, but this little map. Um, Often researchers or businesses want to know how certain words are used across a map and across time. Why? Because some businesses don't always have the same name. It might be Kroger's in, I don't know, Nevada, and Albertsons in California, and a different name, blah, 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 in different locations. So tracking that can be important, but it's not always, your book makes it sound super easy, and it's often a nightmare. But just give you a heads up on that one. A few extra things that I want to talk about that your book doesn't go into, at least not right away, is this parts of speech. I have like a one-line code that I can share with you in the coding demo. Um, what? Oh yeah, I think the quote was, "Unfortunately, no one can be told what the matrix is. You have to see it for yourself." Again, doing the matrix quotes this week. Um, the display, which is part of Spacey, an NLP package, you can kind of break down the linguistics of a sentence. Not only that, you can also break down, nouns, verbs, adjectives. The parts of speech is a very important part of NLP, and it's becoming more important as time goes on for a multitude of reasons. So I just want to kind of touch upon that a little bit more in detail. Named entries or named entry recognition, there's another word on it. That's also becoming more important because as a business, you'd like to know, if I give you all those Amazon reviews and I want to know how many times the word Chevy or GM appears in a positive context this year versus last year, that can become important. What else do I want to mention? Okay. This is one way to measure how similar two sequences are. If you think about it, did I include my name one on here? No, I have a demo here somewhere of this. We have two sentences. How do we measure how likely they are to be similar? And we use this for spell checking. Okay, this is one method we use for spell checking. Now a lot of this is done on machine learning. But this method is super popular at LDA to measure the distance between two strings, two vectors, two systems, or how dissimilar they are. Okay. Now, we finally, that was basically chapter 1. So I told you it was not hard. Chapter 4. A couple things to remember. When we talk about machine learning, at the end of the day, it's just math. It's just statistics. We don't need to get into, the details of weighting and, activation functions and a lot of the math. The point of machine learning is to take you from A to B. The more you know, maybe the more it will help you. But at a certain point, the return on the knowledge of learning ML in terms of business is just not there. Spacey does come with a few pre-trained models. Um, it's hard because I don't want to get a ton into pre-training models because that's where Hugging Face just shines and blows things away. But NLTK doesn't necessarily come with a lot of pre-trained. It does come with data sets, but for certain things, and I thought I could do named entry recognition, but maybe it can't. It's NLTK is a tool that can do a lot, and Spacey is another tool that can do a whole lot. Spacey is, we do parts of speech tagging. Again, I have a demo on that. We do named entry recognition. When we say named entry recognition, remember it can be country too. How often is a word Chevy mentioned with the word Mexico in a positive influence or in a positive manner versus Ford? So Spacey, NLTK, let's see. NLTK is, it can be slow and less efficient compared to Spacey, but it's more suited for academic research environments. I don't know if I would say that. I use it for more prototyping and getting an idea of the data. What am I working with? And Spacey, that can hammer out things in a larger scale, but it's not always as easy to use. Your book uses this, and this is kind of a, I don't want to say a cute diagram. There's nothing wrong with it. It's just not every one of these things is going to happen at the same time. And some of these might not happen at all, and some of them you might spend months on. So source text, identify noise. Well, you can do that through EDA. Remove noise, like the emojis. Character normalization, maybe make everything lowercase. Maybe, however that is for you. Maybe remove apostrophes, things like that. Data masking, and then maybe in theory you have clean text. Maybe that's all you need to take it to. Maybe you tokenize it. Maybe you jump to name nature recognition. Not all these you do all at the same time, and you don't always do it in this order either. Okay, this is just a general idea of how we can clean data and then do something with data. That's a 10,000 foot overview. Say we have some type of data, we need clean data. That's what this is. We need clean data, and we need to do something with the data. You might not always have to do noise removal. You might not always have to do character normalization. You might just have source data, and well, it is pretty good as it is. Let's tokenize it. Let's just go to tokenizing it. Okay, so regex again. I think I have 2 slides on regex. Regex is regular expression. You can Google it if you want. Hopefully, I think Python's a requirement for this class, but we can use it in Bash and in almost every program. Ruby, all programming languages support some type of regex. And in a nutshell, is it's pattern matching. Okay, hey, here's a special character, let's remove it. Here's an apostrophe, let's remove it. Another common issue, we were just talking about data cleaning. On the PC, or let me say on the Mac, there's 2 different types of apostrophe. So you say don't, you have a straight, apostrophe, you have a curly Q one. So you can use regex to take all those curly Q ones and make them straight, make them all the same. So, if you want to know more about regex, there's a couple websites. Did I put it in here? Yes, Regex 101 and Regex XR. Whatever. These are both great sites because you can type in a sentence and say, hey, what you're looking for. Let me see if I can find an example of this. Okay, so it's been a while since I've used this one. Okay, so here is a sentence. You can paste in your own sentence. But let's say you want to find all IP addresses. There's no IP addresses in here, so we'll have to add one. 192.168.1.180. Okay. So here's how the regex would be if you want to find an IP address. So you literally copy this, throw this in a text, throw it in Python or something, and say, hey, I want to search for this, and we'll find all the IP addresses out of a log. Okay. So let's see what else we have here. So that's what's, like I said, my patterns, pattern settings. Make sure we just reload it. I know I don't have any patterns. So let's see what else we have here. Instagram username. So you have you want to look for Twitter names with an @ and a certain number of characters. Boom. You want to see, maybe you have a list of password files. You want to make sure that they're secure. You can do that. Telephone regex. Okay. So you could use this code right up here, wrap around regex, and in theory, it would find valid telephone numbers. So regex. Here's regex 101, very similar, Python. You want to look for all the tags. This is how you do it in the regex. So you just add text, the quick brown 123.456 add a party. So and then tab so this will look for characters from A to Z. So that's basics of regex. The only real way to explain regex is you don't need it until you need it, and then nothing else will do. Yeah, so there's regex for you. Normalization, some thoughts. Some of the things they don't really talk about in the book, but a lot of times it's common to convert everything to lowercase. We remove punctuation, special characters. I talked about the two different types of curly Q and the straight Q, stemming, liminalization, converting numbers to text. So if you say, I'll call you in 5 and put the number 5 minutes, we have to convert that to the word 5, F-I-V-E. Okay. So that's a common normalization things. Dealing with contractions. A lot of times when you normalize data, you want to take don't, can't, won't, convert those all to will not, do not, cannot, things like that. Correct spelling, typos, Unicode characters. Sometimes maybe you don't want email addresses in there. You don't want social security numbers in there. So things like that, hyphenated words. Like when journals or things hyphenate them. You can fix all this stuff either through regex or through, there's other tools that can do a lot of this stuff too. So when we talk about normalization of a data set, this is commonly what we do. BERT is a common tokenizer. That'd be a word. T5 is another one. Spacy's got one. Python, you can just split every word. You regex, use NLTK. So there's a million different ways to do it. Some are faster, some are slower. And like I said, the problem is I had a project where I was trying to get a budget for ChatGPT, where we were sending API data to ChatGPT. And all I had to do was tokenize it and count it. Simple process. Hey, we have 300 million words. Let's just tokenize it and count it. And I can never get my token count and ChatGPT's token count to match. So it's never as easy as it sounds. The general idea is taking sentences and splitting them into words. There's a million different ways to do that. So questions, thoughts, I got 2 more chapters for the next 2 weeks I'd like to get through. Feel free to email me. A lot of you have, and I appreciate that. I'm willing to meet with you on Zoom anytime. Everyone's doing great in the class. Remember, the discussions are doing good. The homework, so far from what I've seen, when some of you submit homework a little early, I'll just make sure everyone's doing fine. I know there's some errors. That's fine. Your goal is basically to be able to download a notebook. Your goal is basically to be able to, get Colab working. But if you have questions, email me. We can set up a Zoom if we need. You can text me. Whatever I need to do to help you. I'm a really big proponent of that. So this is the end. Let me know if you have questions. Thank you.